Would you? Okay, all right. So while we do this, I've been getting grief because I was very fortunate yesterday to win the ThinkPad. I have not owned a personal laptop since I was an undergraduate, and I convinced my advisor to buy me a work laptop out of his grant money. Funny thing is, I ran into that advisor leaving here today because that's Mike Norman, the director of SDSC. So I said, thank you, Mike. And I told him the story of how I gave my last personal laptop to a researcher from Israel who used it for about 4 years until the keyboard broke. And Noan is now got 2 kids and moved on to finance and stuff like that. So, but I've been hearing that I'm not allowed to win this ThinkPad because I worked here 2.5 years ago. I don't know what the statute of limitations is, but apparently this is like the Hotel California. I can never leave. So I'm back. So Mahidar, we got 5 more minutes. I think people time to wander in. This is everyone that went out and had coffee and stuff. So how are you? And how many of you are not from and like new to San Diego? Just like your first trip. Awesome. Thank you for coming to San Diego. I grew up here. I am a native Californian. There are a few of us around. But I left for many years. I joined the Army after high school, and then I went to college at the second worst college in the United States. For those of you who know Bennington, Vermont, you may not know that there's 2 liberal arts colleges in that town, and I chose the wrong one. And so years later, I was looking at the rankings of schools in the format of USA Today, but at the bottom, and I found out that Southern Vermont College was ranked second for screwing veterans and other people and their loans and stuff like that. And what I tell young students now is sometimes dropping out is the answer. So I was fortunate enough to come back to San Diego years later and go, why was I living in the snow? I don't understand that. And to go to UCSD after going to community college. So I have a long history here, and then the good fortune to have worked with Mahidar and gotten many cups of coffee commiserating about the issues caused by those friendly people we call users. Like any enterprise, your users are the cause for your existence. Like your children, they should be your joy and delight, but also like children, sometimes you've got to tell them to pick up the seat. And unlike Bob Sinkovitz, I don't come with a joke cached, at least not a clean one. So,
yeah. Not me either.
Yeah. Yeah, I'm not. Now I get to market for Globus because that was not included in this. Ryan mentioned Globus Labs yesterday, so they'll just give you some filler. Since I've got the captive audience and the congestion voice, which tends to put everyone straight to sleep. I should have done this right after lunch. So Globus is officially a department of the University of Chicago. But if you go to our website, you'll see it's globus.org. We look like a software company. We look like a nonprofit software company, and we drive a lot of our revenue for our services from subscriptions from institutions like places like hopefully UCSD, definitely places like Michigan and others. So we are a subscription-driven group that provide research data management services. We have an OAuth OIDC layer that ties into things like InCommon for authentication. We allow developers to secure their own REST APIs using that infrastructure. And then we have, of course, Globus Transfer, which is the managed, reliable, fire and forget, high-speed, secure transfer mechanism. It also includes features like sharing out collections of data to groups and researchers. That's the product team. And then there's the lab side, which is where Ryan and folks like Kyle do a lot of the innovation that eventually hopefully flows in. Certainly it has in the case of the work that Ryan did in Automate. But then there's the professional services team. That's my group. I have a set of engineers and developers that get embedded into projects to do integration work. So I have folks that work on Exceed, which many of you may be familiar with. If you know JP Navarro or Lee Liming or Eric Lau, they all work for me. I need to step up to the mic. All right. So they all work for me. And then I've got others that work on various projects supporting it. So the product team, if you download Globus Connect server, if you run transfers, you're using their services. If you need help on a project and you have a grant and you have money and you'd like to share it, call me up. I like working with people in research. So, all right.
So I was going to introduce Rick, but he's introduced himself. But I'm really happy to see him back here. Among other things, I think Rick's responsible for Singularity being on Comet. We got started real early, 2016, I think. So I'm happy to see you back here. And you're going to talk about managing large-scale cosmology simulations with Parsl and Singularity. Thanks.
Yep. Thanks, Maidar. So the history is that with Singularity, when Comet supercomputer deployed, it was at the same time that machine learning was becoming very, very prevalent, and TensorFlow. And TensorFlow was being developed heavily on Ubuntu and Ubuntu laptops. And like the story yesterday of as a user, I want to, as a user, a lot of people wanted to run TensorFlow on Comet. And the issue was Ubuntu was at a later version of libc. And as I tried to explain to my 15-year-old son who doesn't program last night, when you have a libc incompatibility, you really just can't shoehorn that in. That is not something you can uninstall and put a newer version on. And fortunately at that time, Singularity had come out and essentially solved our problems within a day. So Greg had approached me earlier about it, and I'd had a telecon, and I was like, I don't really understand this. I don't think it solves our problem. And then I was like, 6 months later, wait a sec. And so we tried it, it worked, and I recognized that this fit the need for HPC systems at the user level very easily. And I think sometime that was actually before PERC in New Orleans, I believe. And so as somebody reminded me yesterday, I ran around screaming and said we need to have a BOF. And Greg Skyped in with guitars in the background on the walls and wowed everyone with the capabilities of Singularity. And here we go. And so now when I got to UChicago and Argonne and Globus, and folks like Ryan and Kyle were dealing with how do I execute these things on a variety of systems, I'm like, Singularity, please try it. Push the admins, convince them you need this. And if you looked at the recent press release for a different complete run on full machine use of Theta at Argonne, you'll see that it's solved some problems. So what I'm talking about here today is, I'm talking about Parsl. And Parsl is an auto-parallelization tool that's written in Python and developed out of the University of Chicago and Argonne by Carl Chard and Yadu Babuji? Yeah. And then they worked with a bunch of folks tied to Salman Habib and Katrin Heitman on simulating LSST images to prime the pump for the LSST, the Large Synoptic Survey Telescope that is going to be built. So let's talk about both of these. All right, so the LSST, if any of you are involved with research science and people talking about data at scale, this is the data boogeyman. This is the thing that is going to pump out all the data and blow up our internets. And they're not really kidding, because it's going to take a full survey of the sky every night and generate 15 terabytes a night of raw data. And the critical part is this data actually has to be evaluated, because it's going to do awesome stuff like look for supernova and point other telescopes at it and say, hey, maybe you should look over here and capture this light curve so that we can look more deeply at how the supernova are going off. It's also going to do really cool stuff like, hey, is that an asteroid headed towards Earth? So near-Earth object detection and transient object detection means that it's critical that we have a robust analysis pipeline. Now, the thing is, we don't have the telescope yet. We don't have telescopes that can generate this kind of data. So how do you know your analysis pipeline works? Because you don't want to take a year or two and perhaps miss that first asteroid or supernova or whatever it is before it happens. So what they've been doing is trying to generate synthetic data to prime the pipelines and have all that ready and waiting to go for first light. When you turn on a telescope and you capture the first photons coming from the sky, that is referred to as first light. By the way, like John Towns, who led before me, I'm a failed astrophysicist. So this is very enjoyable for me. All right, so the thing about LSST data also is it's going to happen at various scales. And this is common for a lot of science projects when I describe it. If you think about raw data processing, right, the LSST core team is going to be responsible for that. They're the ones that are going to build and maintain the data pipeline that produces the initial data products and then creates data releases. Everyone's heard of the Sloan Digital Sky Survey, they did that. It was a large team, but it was relatively small compared to the next level, which is the science collaborators, the people that are close to it who are going to be ready to jump on those data releases and aid with those data products. So you're talking about going from tens to maybe hundreds and then thousands. There's going to be the Sloan Digital Sky Survey. If you look it up and you see the number of papers that have cited it in its data releases, it is stunning because they opened up the data. The proprietary period was very minimal. There was one or two publications that came out, but it was all about showing the power of opening data for the broader good. So how do we think about data tools that can be reused throughout these, starting at the very beginning with the raw data processing, to the point where I guarantee you, it may already be happening now, high school students, undergrads, et cetera, will be taught and trained in various methods of science using this data. It'll start trickling out via astronomy summer schools, and then some bright person is going to say, I'm going to take this back to my high school, and I'm going to teach somebody. Happens all the time, and it's wonderful because people do want to be really engaged with direct science. So, as I said, we don't have the actual data yet, and we don't have the actual telescope. But what we do have is simulations. And we have large, now nearing exascale simulations of the universe. And these simulations can generate structures of the universe at resolutions that are the level that we want to detect with something like LSST. When we want to study dark energy and look back through time at the history of the universe and see how things have changed in terms of the expansion of the universe, other characteristics, we can model that. And then we can try and generate images to see if the scientists can, from the images, determine the initial structure of the simulation. So to do that, we want to go from something that is absolutely a simulation. This is from the Virgo simulation done in the last century, and which is largely just looking at particles of dark matter and whatnot, to go from something like this, which looks a lot like a real picture of the sky but isn't. For a long time, scientists have been working on things like GalSim. This is where you can generate a catalog. Think of a table of galaxies and galaxy clusters that have things like the orientation, the shape, the color, the age, the morphology, et cetera, of galaxies, and then they generate point spread functions or other patterns of light onto a synthetic image. And so they're just either ray tracing or stacking these images to splat them up against something. Of course, they're doing it not just in the RGB alpha color space, but perhaps in other color spaces, because you're also dealing with the expansion of the universe where weird things happen, like ultraviolet becomes visible, and other things become radio waves, because that, as the universe expands, the wavelength of lights go along with it. The story is, we start with a simulation. You do a bunch of analysis at large scale on the simulation. You identify the clusters of galaxies. You start to have probability distribution functions for the appearance of galaxies within that. And you generate a synthetic catalog. And you say, I think there's a spiral galaxy here. I think there's a barred galaxy here. I think there's the mice galaxies, which collided a long time ago, over here. And you build this catalog. And then you do an image simulator that not only creates the idea of the photons coming in, but all of the behavior of the telescope, right? The telescope is not a perfect instrument. It has errors. It's got a CCD. It's got readouts. It might have a bad pixel that day. It might, not be able to turn. It might have stutter. The atmosphere. They fire lasers into the sky to help guide telescopes and stuff like that, and counteract atmospheric effects. And you've got to put all that into it to make the final image as accurately bad or real as possible. So that way, when you're inputting things into the LSST data management stack, it's not ideal, it's not perfect, and the scientists don't know what's there. And so if you're going to do transient object detection, and somewhere in this pipeline you've injected a near-Earth object or the initial part of a supernova, you put it in, and it goes through, and now you've got synthetic observations. And you can do science. And you can look at the images and you can try and extract the underlying cosmological parameters of the simulation, or you can try and extract the near-Earth object. So imagine that we have a constellation of the Mermaid, and the constellation of the Mermaid passes all the way through. Eventually, at the other end, the person should say, all right, yeah, oops, boom, found her, all right? So that's the goal. So how do we pull this together, right? So that's the end result. But this is not trivial software. This is not just I'm going to run a Python script. I got one piece of C code that's going to do everything. We're starting with massive simulation output that's run at full scale on machines like Theta, and will be the targets of the Coral program and things. And now we've got to generate these synthetic images from the catalogs. I think you might recognize some of the comments here when we think about how software is created by teams nowadays, is that a lot of it is assembled, right? Yes, we still have a strong need for Fortran. I will argue with you about that. We have C. We are spending a lot of time vectorizing code. AVX made a difference. We talked a lot about GPUs. We have things at various scales, but then we've got to have the high-level stuff that glues it together. And that's where Python comes in. That's where we do our bash scripting. We're pulling data from this tool to that tool. We're sometimes sending it across the country. We're using web services. So we're tying all these things together. And the idea here, like we talked about, is the presentation yesterday about making parallel and distributed computing accessible. We got to make it easy for people to use. It's not a niche requirement. It's not just folks like myself, old white guy with a gray beard, sitting in front of a computer. It's everybody who should be able to approach this, and we have to give it to them because everything's maxed out. I'm sorry, but the smaller you made the chips, the hotter they went, the faster the frequency, the more power they drew. There's a limit, there's a cap on it. We have to use distributed and parallel computing, and we have to keep scaling if we want to do the analysis. And then we think about collaborations. We can't have a single brain trust within the world where we take all the people working at a problem and stick them in one place and say, all right, work together on this one code base. People are all over the place. It's collaborative. The people themselves are distributed. And the rise of GitHub as one of our primary tools for science shows how we can decompose and make components out of various pieces of software. And we got to pull it back together. I do think GitHub, by the way, was the right choice, and if any of you know Matt Turk, he still owes me $20. So, all right, Parsl and Singularity. So you have two things here. Parsl, which, by the way, if you've heard of Swift, was another tool for parallelization. Parsl is derived from that, but Parsl allows for defining parallelism and saying, this portion of my code, and any of you who've worked with OpenMP, OpenACC, other things would recognize something like this, but this is in Python, which is better because it's easier. It's a way to say this piece of code can be parallelized at runtime. And once you have that, what we use for some of it is Singularity, so that that portion that can be parallelized might be encapsulated in a convenient container that can be deployed on the system, similar to some of the ways that Ryan described with FuncX, which, by the way, uses Parsl under the hood. Parsl has the concept of an app. So if you have your section of the code, and if those of you who haven't seen Python and Python decorators, this is your pound pragma for Python. It's an @ symbol and the decorator function, and this declares the next section of the code, in particular a method or function, as being, in this case, parallelizable by Parsl. And there's two different kinds of apps. There is the Python app, which would be a Python method that could be then be encapsulated as a pickled object to be interpreted elsewhere. or bash, literal bash, command line type of apps. So here's an example of a hello world. And the apps, when you're executing them, imagine them, you have them in, for example, a Jupyter notebook. These apps will return a future. So think lazy evaluation. You want to call this, you know that it's chewing on data somewhere, but until you go to evaluate that result and depend on it, you can just keep going along and going along and going along, and it'll block eventually when it's like, no, I'm still waiting on that result from across the country. And the nice thing about these decorators is Parsl is abstracting various things for you that I'll go into, like what computer you're running on. Any of you with your laptops out and want to tune in for a sec, you can try Parsl. I made a convenient bit.ly link, capital P Parsl, capital B binder. And then you can, if anyone's got their glasses on, you can instead go to mybinder.org/v2gh Parsl, Parsl tutorial master. Or you can do capital P Parsl, capital B binder, and test Parsl within a binder app. This is an example of wrapping a protein docking code where you have a bash tool, which is a Docker application wrapped. And by the way, if you're not familiar with Python 3, this is the new text kind of printf or printf format. I can't say I'm a fan. But then inside of that, you would be able to call it like this. All right, a little bit about how Parsl works under the hood. So our favorite term in computer science and in a lot of other fields like data provenance, directed acyclic graph. We want to look at the code and identify dependencies so that we can do things like say, all right, this blue block is dependent on the execution of these next two red blocks. So I am going to start the blue block, launch the red blocks, and then I can go on and look for the next stages of the graph, which are the green and the purple, and I can trigger their execution, but I can run those in parallel at the same time, and then at the end, I can pull them all back together. So Parsl's all about managing the digraph and pushing it out to systems. Now, again, I said that Parsl abstracts the systems. They're execution provider independent. A lot of the team's work goes into writing executors for target systems so that you have your Parsl app and you've got those decorators and that's all you need to know, because the model is that you have an executor on the system. By the way, if you want to know more about this, ask Ryan, because I haven't actually run most of this. But here's a lot of your favorite systems, like some of Exceed, for example, Jetstream. I'm sure somebody may have run it on Comet. If not, we would be glad to. Blue Waters, Theta, Cori. We do a lot on AWS and Google Cloud. Mira. Is that TAC? And Summit. And OSG. And so and Parsl is using, a lot of cases, containers for that per app execution and reuse. So especially like when you think about the Bash app, containerize it and then just reuse it in different places. Makes it very easy to port and move it. We use Jupyter Notebooks a ton. They're a convenient way to drive it and to demonstrate and teach it. We also, so Ryan started touching on this yesterday. Different needs have different loads. All right, so some of them are high throughput. Some of them are where you have a weak scaling application where you just want to throw more cores at it and each one's working on a single piece of work, or you want to iterate on small pieces of data and you can distribute it broadly and they have different requirements. In the case of the one that we're talking about with cosmology, it's more of an extreme scale. We did a very large run though, but we also use it for interactive and real time. So if you want to do different machine learning models, evaluate training models with a set of parameters, parameterization survey, you can go interactive and have a set of nodes that you're constantly firing stuff to and launching them. And the cool thing about the Parsl abstraction is, like we think about running it at Argonne, we have a Kubernetes cluster called PetrolCube. That's where DL Hub runs. We also have Cooley. We also have Mira. We also have Theta. And so that gives us a heterogeneous compute infrastructure to select the best one to run on. And with Parsl, we can target the right one for the right workload because I don't see that at the front. I just select my compute environment. For those of you interested in performance, there's the term strong scaling, where you want it to go faster based on the same problem size. Parsl scales very well. If any of you are familiar with Dask, or can't remember what the other one is, tends to do better than that. Parsl is just well architected, and a lot of energy and thought has gone into the performance. Weak scaling, also, there's the comparison to some of the other ones like Fireworks and Dask. Weak scaling, where you want to keep the time the same but make the problem size bigger. Again, Parsl is doing very well. There's other things you can do with it, is like the resource abstraction. That's where we try not to make the user think about where they're running, if at all possible. The fact that Parsl is managing the execution and that little chunk of work is spun out, monitored, and then brought back means that it's fault tolerant. You can actually have it retry that if it fails without the user having to be aware of it. Right? They're waiting for that lazy evaluation until they actually depend on it. So Parsl has a chance to go out and redo that node on the graph if it fails. As somebody who managed a system where people ran large-scale HPC jobs and parallel jobs and actually haven't been a user who's run large-scale HPC jobs, the fact that one component can ruin my month is really frustrating. And that is an exascale problem that we're all facing. Parsl is not going to solve that, but at least identifies it as an issue and addresses it. You can actually execute in different locations. So if you have a notebook with two different types of workloads, like you're coupling an analysis to a simulation, you can do it. And monitoring elasticity, you can tell what's going on. I talked at the beginning about Globus, what Globus does in terms of auth and transfer. That's what Parsl is using under the hood. So all the authentication is done through Globus auth, and then the input data, sometimes the apps themselves, are staged via Globus. And Globus can be very, very fast at times, actually most of the time. And so it can get the app to the node and execute it, and then it brings the results back in the same way. In a lot of cases, what you're seeing is pickle files flying around everywhere for that execution. And pickle files are okay in this context. But again, you can see the advantages of containers is I don't want to be in Python dependency hell if I'm trying to run in two different places. If I have got a class and I pickle it and I send it to TAC and I send it to SDSC, I want it to run in the same place, and I don't want a different attribute in that class ruining my month. Jupyter, it's Python. You do an import Parsl, you go to town, you set your config, and you launch it. And then reproducibility. Parsl can rerun that graph anytime. And think about the case of the cosmology tools. IMSim that generates the data from GalSim, which then gets executed all by Parsl, is being made by tens of people in various locations. Being able to say, give me a container that I can take and rerun saves the effort of how do I deploy all of these tools and all of these different systems in a reliable manner. So you don't only deal with IMSim itself, but what if it has conflicting dependencies with GalSim, a key component, or whatever cataloging tools Salman and Katrin's team are using. So you have isolation, portability, all the reasons we're here and we're using this. So here's the flow that got executed. You have the various catalogs with the various sensors that are going to get activated. You break those up into work and distribute them across the system, and each individual container is working on various sections to create the final images of the night sky. This is what Theta looked like when it was running. So as you can see, LSST, ADSP, something, dark energy survey, Singularity was running on almost all of Theta. And as I mentioned a few weeks ago, there was a press release out. Perhaps somebody like Ian was involved with the release of this from Argonne about Singularity running on all of Theta. It was actually a different run. It wasn't this one. So Argonne is using this heavily. And I got to follow up with Kyle on this one because when we blew our allocation at Argonne, we moved to NERSC and we ran on Cori, and someone helped them convert the Singularity container into something that Shifter would run. I am in conversation with Shane Cannon politely about evaluating Singularity for Cori. NERSC has been a slow adopter. Doesn't mean it's going to go anywhere, but again, never underestimate the power of institutional jealousy. So Shane is a reasonable person, a very smart guy, and I think it's more about bandwidth limitations than actual any resistance. Oh, by the way, because I don't know if Sterling's made it yet, but I work for E3SM, the DOE climate science project, and one of the reasons I'm here is because we've begun containerizing really gnarly analysis codes and coupled models and stuff for portability. All right, so Parsl and Singularity, it's simple. You know, we understand it. As I told Jeff Pummel yesterday, you know, it's not going to take you all afternoon. It's going to take you 5 minutes. You're going to just install it, run it, and it's going to work. Scalable. As we see, it runs faster often for various reasons on different systems, and portability. I've got a guy on my team who is working on getting Zero to Jupyter Hub running on our Kubernetes cluster. Once he finishes that, we're going to work on getting the OCI layer installed so that we can start moving containers from Theta and Cooley over to PetrolCube seamlessly without having to convert them in and out of Docker format. And with that, if you have any questions or you want to follow that bit.ly link, it's great to be here.
Thanks, Rick. So questions for Rick?
Oh.
I'm going to get one here and then go the other way.
In the initial slides, you mentioned about the 15 terabytes data per night. What's the usual lifetime of that one night data?
So my understanding of the LSCC data pipeline is that 15 terabytes, most of it will actually be cached at the US, that there is a pipeline to immediately replicate the data and stream it out to data centers within the US. So they've got a data center in Chile, and then they've got a data center in the US, but they have to process all of it within the night. So they have analysis systems to go through and do the initial calibration, et cetera, and then start doing the evaluation for things like near-Earth objects or supernova, basically transient detection, because everything else can wait a bit longer.
So after a night, that 15 terabytes is deleted. Is it fair to say?
No, I don't believe so.
That's
they're
what I was
keeping a
asking.
lot of it. Now, I believe there's a data reduction step, but they're trying to keep a lot of the close to raw data for the life of the project. The question is, does it go from 15 terabytes down to 5 terabytes? And then they're keeping that. But yeah, the data storage requirements for LSST are gigantic.
Okay, thanks.
You got two more on the other side.
Okay.
Jerry, just hold on a second.
Hey, Jerry.
So, hi. Does Parsl imply that each process is embarrassingly parallel, or can it be multi-node, or shared
Parsl,
memory, or?
so is Parsl assuming embarrassingly parallel? No, Parsl doesn't assume any of that. Parsl, basically, the individual apps, I believe, Ryan, we did with Parsl GPU apps. So some of the single apps were actually vectorized code executed via CUDA. But because it's got the graph, each individual section, in that case, once you have the DAG, you know the nodes that you can execute independently, and you can execute all of them within the same echelon or tier of the graph at the same time. So you just basically are traversing the graph and chewing through your dependencies as you go along. And so I think in this case, it's a question of granularity. You have to choose how to decompose that graph so that each unit of work is approximately the right size to fill your pipes. So it's a different model than our thinking in terms of MPI, where we've explicitly declared the graph, and we all know how that suffers.
Your code has to be organized that way for that to work.
Yeah, you do. You have to decorate your code. It will determine the graph. But yeah, like MPI, like hybrid programming, the more expertise you bring to it, and even if it's gut feel, the better you'll do. But for simple cases, you can easily parallelize your methods from the get-go.
So, excuse me. So my question is, earlier you mentioned Fortran. So I want to know, what are you stuffing into the containers, and how big are they getting for a real astrophysics scale code? And do you couple to the Fortran code, or are you requiring that all the legacy code be rewritten in Python so it's newer model, more lightweight?
So the question is, so I made the crack about Fortran code being necessary. So in the case of, like, consider you have two different types of decorators inside of Parsl. One parallelizes across a section of Python code, and as we all may or may not know, a lot of Python code is not written in Python. A lot of the underlying Python code is NumPy or something else where somebody said, damn, this is slow. And they realized that it's not that hard to rewrite it in C or Fortran or something else. And in fact, a lot of NumPy is written in Fortran. So if you decorate something that's calling NumPy, those dependencies for the Python code will be packaged and shipped out. Typically what we have is an existing container that has all the dependencies anyways. So like if you're working in a Jupyter notebook, you try to have that Python environment match the environment on the system so that you're not going crazy. And then that NumPy array that's getting evaluated in Fortran, it's already there. Now, in the case of something like this, you're using the Bash app where IMSim, a relatively large, complex piece of code that's a standalone application on its own, can be called via Bash. So you have a container that you can execute via the command line, and you're actually parallelizing across the execution of a command line application, but doing it from within a Jupyter notebook. And you're just saying, this is a Bash app, you need to call this is going to be the input data, this is going to be the output data, and send it out and bring it back to me. So you can parallelize at different levels within a Python method, or at the level where you're actually calling a separate application on a distributed system. And Kyle would love to talk to you and work with you and Andrea to test this. Is Andrea here? No, of course not. All right. So if Mr. Zonka was around, we'd love to work with both of you to learn more about this and get it deployed on Comet.